this is the one that you have studied before during the third year. The purpose of having coagulation and flocculation process in water treatment is to remove the turbidity. What is turbidity? By definition, turbidity is the clarity of water. Is the clarity of water, the ability of light to transmit within water. If you can see clearly, look at the beaker down here. If you can see clearly through the beaker, meaning to say that the turbidity is low. So comparing between these two beaker, you can see that the one on my right side is 80 MPU, and the one on my left side is low turbidity. So this is the reason why that we have to conduct the process of coagulation and flocculation process. Okay, how does this process can be conducted? In conventional water treatment plant, this process can be conducted or can be done through addition of the coagulant. What is coagulant? Coagulant can be defined as a binding agent. It works like a binder. What to bind with what? What substance can be bind with what? The first one is when you add coagulant, for example like alum, the most common coagulant is aluminum sulfate. These are the most economical coagulant that being used in water treatment plant. When you add coagulant into untreated water, because this is the first process, the major process before coagulation and flocculation is the preliminary treatment, which includes the screening process. So that during the coagulation and flocculation process, we believe that there is no more large debris. So during this process, the raw water to be treated should only comprise of uh, should only contain hard suspended solid. Okay, suspended solid. For this reason, when you add coagulant into the raw water, it will act as a binding agent. Coagulant is the positive, is the positive charge, while the pollutant to be removed, especially the suspended solid, or the dissolved solid, they are known as colloids, negative charge. So when negative means positive, they are attracted to each other. Okay, so during coagulation process, this is what will happen. So coagulation process can also be defined as the addition of coagulant into raw water. Okay, next, flocculation process. What is flocculation process? Flocculation process can be defined as the rapid mixing process. Rapid mixing process are extremely important. After addition of alum, without rapid mixing process, it will be difficult, or it will take longer, for the alum to bind those pollutants, to bind those impurities. Okay, so that rapid mixing during flocculation process will further expedite the formation of the flocks. Okay, the formation of the flocks actually does happen during addition of alum, which is during coagulation process. But in order to allow one flocks to combine with the other flocks is require rapid mixing during a flocculation process. This is the overall process. Addition of the alum, in green, red colors are the impurities. So the binding process between the negative and positive charge. The positive is the coagulant, which is in green. The impurities is a negative charge. Okay, in order to promote the attraction between these flocks, we have to employ the flocculation process, because only by employing the rapid mixing, the flocks will be bind to the other flocks. Otherwise, we will have only smaller flocks. So it will settle to the bottom part of the tank, but it will take some time. Okay, regarding on this process, uh, the obstacle is to have a shorter retention time during coagulation and flocculation process, as well as sedimentation process, which is the following process after flocculation tank. Nevertheless, the water operator are looking forward. Currently, there are few water treatment plant who has been employing the micro sand technology. Why do they have to employ microsand technology during coagulation process? Yeah, when the microsand are being combined with the alum, so that once microsand combined with the alum as well as the impurities, the the flux will become heavier. So the heavier the flux, the faster it will settle to the bottom part of the tank, so that we can reduce, so that the detention time in flocculation tank as well as the sedimentation tank can be reduced. So we would like to promote to have a heavier flux. That's why uh, the role of the alum is to bind the impurities. However, binding the impurities sometimes is not sufficient, for them to settle faster in flocculation as well as sedimentation tank. Is require other agent, which is the role is to promote, faster settling process. Okay. Alright, so basically coagulation process, there are two major forces. The first one is repulsive forces, which is zeta and electrostatical process. And the second one is van der Waals forces. Van der Waals forces are the major forces, the attraction, the attractive forces during coagulation process. Okay, so okay, how to estimate, the optimum dosage, when we would like to apply alum, in water treatment plant, we have to know what is the optimum dosage. We cannot we simply put the alum into the coagulation tank. So there are two main reasons, why we have to get the optimum dosage. The first one is, the higher, sometimes the higher the concentration of the coagulant added into water tank can cause pollutant. Why? Because the optimum dosage is not always the highest dosage. It's not always the highest concentration. The second one, water treatment operator definitely is looking, for the best dosage, which can, for the least dosage, for the lowest dosage to be added into water treatment plant, but it can treat the water which comply to the WHO standard, because it can save a lot of money. So that's why in most of the water treatment plant, they are equipped with the jar test. So maybe we can spend a few minutes to watch one of this video. I believe that you have watched this before during our lab session, during your online lab session, 2 years ago. Okay, this video is in Spanish. Not this one.
Stop! Don't drink that. There's chemicals in the water.
Not this one. I'm looking for the one in Spanish, but the subtitle are written in English. Hmm. I can find one.
This is a very basic overview.
Oh, not this one. Oh, where is the video? We have 4 video here, but I would like to share with you only one of them.
Telling you.
Oh. Okay.
Flocculation and coagulation are fundamental for wastewater treatment and were already used by the ancient Egyptians in 1300 BC. This sample of muddy-looking water from a paper mill has a very high turbidity due to the presence of many suspended particles. Adding flocculants will cause that the small particles clump together to bigger flocks that settle down. So let's have a closer look at how flocculation and coagulation work in detail. Turbidity of muddy-looking water is caused by two types of particles, organic and inorganic. Organic particles are, for example, algae and bacteria, whereas inorganic particles are, for example, clay and silt. Both particle types have in common that they are able to float because they are too small to settle by gravity. Suspended particles that are too light to settle down are called colloids. Almost all colloids have negatively charged surfaces. The negatively charged surface will attract positively charged ions in the water, so the colloids form a first layer. The effect is very similar to magnets. Like poles repel, but opposite poles attract each other. Over time, colloids form a second, diffused layer with positively and negatively charged ions called a double layer. The double layer creates a responsive force which prevents two colloids from stacking to each other. The colloids stay suspended in water and move around to avoid collision with other colloids. To overcome this behavior and to clump colloids together for particle settling, flocculants are used. Typical used flocculants for particle settling are alum and ferrix. Alum and ferrix are ideal as flocculants because they form a high number of ions when they get in contact with water. These ions will bind together with the colloids and neutralize responsive forces. Mixing the water allows the colloids to stick together, to form bigger flocks and settle down to the tank bottom. Within wastewater treatment plants, the flocculation
Okay, yeah. So in short, when you add coagulant in water treatment plant, the colloids will combine and form flocks. So what is colloids? Colloids comprised of the suspended solid. It can exist as the organic or inorganic substance. Okay. Okay, so that's all. Okay, so a very quick revision. You have done this before. Design a flocculation tank for the following information. The volume of the water to be treated is 1950. Basic design. Length to width ratio equal to 3. Depth equal to 3 meters. The freeboard that you have to allow is 0.8 meters. Compute the length and the width. Compute total volume of the tank. Compute the working volume of the tank. Okay, how to solve this problem? Size of the tank. Very simple, very simple. Okay, so volume of the tank given to you is 1950. So you are also being given that L is equal to 3W. This ratio is given in the question and D is equal to 3 meters. So knowing the equation that volume is equal to L times W times D, so 1950 is equal to 3W. Why? Because L is equal to 3W. So you solve for this equation, so it's equal to 9W to the power of 2, and you will get W equal to 15 meters. So L is equal to 3W, so L is equal to 45 meters. So D is given as 3 meters. So first you are to calculate the length and the width. And second, the total volume. What is total volume? How to differentiate between total volume and working volume? In aerobic treatment is perfectly fine because it's an open treatment. However, when you are dealing with anaerobic treatment, which is the system are fully covered, you cannot allow any oxygen goes into water treatment, into the wastewater treatment plant. For that reason, working volume are important to be figured out to allow some head space. This is to avoid explosion. Okay, so total volume in this case is equal to 45 times 15 times 3 plus 0.8. What is 0.8? 0.8 is the freeboard. Yeah. So you have to consider this, yeah, when you calculate for the total volume. Why? Because it is different as compared to working volume. Working volume is 45 times 15 times only 3. Yeah, you don't have to consider the freeboard. The freeboard meaning to say that the extra space, yeah, they have to be added into the depth of the tank. And the depth of the tank in this case, if you are considering only the working volume, so it's 3. But if you are consider the head space, meaning to say that the total volume, you have to plus 0.5. Yeah? The value of the freeboard normally is 0.5 to 1 lah. Yeah. Right. That's all for this chapter. Next, we go to the following chapter, on the sedimentation process. Yeah. Yes, sedimentation process. Okay. This is also revision, yeah, but to have a quick overview before, yeah, because our major focus today is on C, yeah, filtration process, because you have explored before, yeah, during the third year on environmental engineering subject. Nevertheless, yeah, in this course, you are going to explore about deep sand filtration, yeah, as I mentioned just now. So before we go to filtration, we have to study a little bit, on sedimentation process. Very quick overview about what is the processes involved during water treatment plant, during water treatment process in water treatment plant. Again, any substances left, yeah, in treated water which doesn't comply to the limit set by WHO, so it has to go to tertiary treatment, yeah, advanced treatment process. Yeah. So again, uh, after the treatment process, after water treatment process, the purpose is to produce a potable water. What is potable water? Yeah, it can be defined as water which is safe to drink, suitable for domestic purposes. It should be odorless, it should be tasteless, and it should be colorless. So that's how we define potable water. But if we cannot produce a potable water using conventional treatment system, this is what I call as conventional, chemical addition, coagulation, sedimentation, filtration, and disinfection. These are conventional treatment process. For that reason, this is where that the tertiary treatment is required. Okay. Alright, this is the solid contact clarifier tank, in sedimentation stage uh, during sunrise, and this one is the photo during sunset, and just to share with you the photo. But the components that we would like to remove, during sedimentation process is the suspended solid. But during coagulation and flocculation process, the purpose is to remove the turbidity. So how do we differentiate between these two parameters? Yeah? Turbidity is a part of suspended solid. Yeah, but turbidity is a part of suspended solid, but uh, sorry, yes, correct. But suspended solid is not a part of turbidity. You know why? Because turbidity, it doesn't comprise of the sediment. Very small particles, very fine particles, they are classified as turbidity, and they normally exist. They normally floating, in water. But when you are talking about suspended solid, it is including the sediment, the bed load, the sediment. So that's why I said turbidity can be a part of the suspended solid, but not suspended solid. But suspended solid is not part of the turbidity, because suspended solid you can find more, in raw water. The concentration definitely will be higher lah as compared to the turbidity, due to the presence of sediment. Okay, so the rest of the colloids, which cannot be removed during coagulation process as well as sedimentation process, are going to be further improved, further removed during filtration process. Okay. Okay, by definition, the purpose of having sedimentation process is to allow more time, to allow more time for the suspended material, the suspended matter to settle to the bottom part of the tank. So these are the major purpose of having sedimentation process. After rapid mixing process in flocculation, we know that most of the flocks will settle to the bottom part of the tank. But due to the short retention time in these two tanks, coagulation as well as flocculation, we need to give ample time for water to flow into sedimentation tank and ample time for the suspended material, the remaining suspended solid to settle to the bottom part of the tank. For this reason, there are two major tanks which will allow sludge to settle to the bottom part of the tank, which is flocculation as well as the sedimentation tank. Okay, so these are the real photos of water inlet, flocculator, clarifier tanks, clean water and clarification tank. Alright, nowadays they have combined some of the water treatment plant. They have combined flocculator as well as a sedimentation tank. But it will work. It will not work in parallel lah. Still flocculation followed by sedimentation. Okay. These are the most common sedimentation tank, rectangular sedimentation tank with effluent with structure visible. So these are the sedimentation zone. We have four major zones in sedimentation tank: inlet zone, settling zone, the sludge zone, and the outlet zone. Those stubborn suspended material which cannot settle to the bottom part of the sedimentation tank will flow through with the water, with the treated water into the filtration process. Okay. Alright, factors that can influence sedimentation process including the size, the shape and density of the particles. That's why when we calculate the settling velocity, if you still remember, we have to consider the specific gravity of the particle. We have to consider on the shape factor of the particles. So because the the heavier the particle, it will take some time. The lighter the particle, it will take some time for them to settle. Normally in water treatment plant, they they shall do a quick check on the settling velocity. So normally to check the settling velocity, they will have to choose the smallest particles that to be removed in water treatment plant, so that if the smallest one have a good settling velocity, meaning to say that the bigger particle should be having no problem, then the heavier particle should be having no problem to settle to the bottom part as in the sludge zone. Okay. Nevertheless, when we come up with the design of a sedimentation tank, we always put consideration on the length of the tank as well as the detention time. I repeat, when we design for a sedimentation tank, there are two major parameters. The first one are the length of the tank. The second one, the detention time. Okay, the depth of the tank, it will not influence the settling rate of the suspended solid or the colloids just now. The, uh, the sedimentation process, the settling process of the suspended solid in sedimentation tank are mainly governed by the length of the tank as well as the detention time. The longer the tank, it will improve the settling rate, and the longer that you leave the water inside the tank, definitely you will get a better quality of water. The detention time, meaning to say that how long you leave the water inside the tank without any activities, so that will give some time for the suspended solid to settle. Alright, the sedimentation efficiency does not depend on the depth of the tank. The area, that's why I said the length are still the major parameters when designing for a sedimentation basin. Yeah, so these are the round cylinder of clarifier sedimentation tank. Most of the conventional treatment system, the sedimentation tank are rectangular. Yeah, but there are few newly developed sedimentation tank where in the form of circular like this, which is known as clarifier. Okay, let's see what is the advantages of having this kind of system. When you employ a circular clarifier, you will have two arms. Yeah, you can see the bottom's arm. Yeah, will be used to scrape or to remove the sludge. Which settle to the bottom part of the tank. On the other hand, there will be another arms. Yeah, the top's arm are known as skimmers. Yeah, the function of the skimmers is to remove the scum layer. Yeah, so having this kind of system will further improve the quality of water, because uh, there are two ways, yeah, for for the sludge, whether the sludge which floating on the surface or the sludge will settle to the bottom of the tank. Okay, these are the cross section of the clarifier. You can see these are the scum outlet. The small bubbles contain sludge which is float on the surface of the clarifiers are known as scum. Yeah, so they are normally being removed using the rotating arm. Yeah, and also we do have the bottom arm, which is known as the sludge rake, and these are to remove the sludge. Okay, so if you can see the movement of the pattern, yeah, of the water movement, this is the influence, yeah, from the flocculation tank, yeah, goes into the clarifier. Yeah, so this is the point of effluent goes into the filtration system, and there will be one sludge discharge outlet. Yeah, all right. This is again the example design for a primary sedimentation tank. Yeah, the average flow rate, yeah, at small municipal water treatment plant is 2000. Design two rectangular primary clarifier with a channel of 6 meters. Use a minimum of two clarifiers. Given an overflow rate, yeah, surface overflow rate of 40 meter cube per meter squared day. Okay. Again, I would like to repeat, yeah, surface overflow rate, they are not velocity. Yeah, because why do we need to use a surface, the terms of surface overflow rate? Even though when you cancel out the unit here, you will be getting more or less the unit like of velocity. Yeah, because by definition, you are actually these parameters representing the flow of the water per area of the tank. Yeah, that's why they are not exactly a velocity, even though when you cancel out unit, it will be velocity. Yeah? Right. In this question, the settling velocity is given, which is equal to 0.003 meter per second. Now you have to compute the tank volume as well as the detention time. Okay. Okay, so this is the solution. The Q is given is 20,000 meter cube day. The surface overflow rate is given as 40 meter cube per meter square day. W is 6 meter, D is equal to 4 meter. Probably D is not given. Yeah, this is an assumption. Volatile solid, sorry, the settling velocity is equal to 0.003 meter per second. Okay, first, you calculate the required surface area Q over SOR, because Q over V is equal to A. So you solve for this equation, you will get 500. So this indicates that in order to treat 20,000 meter cube per day, is a required surface area of 500 meters squared. But in the question, it's clearly stated that you are to develop two clarifiers. That's why here I divided into two. So each of the clarifiers, the surface area is equal to 250 meters squared. So W times L 250. So W is given as 6 meters. L is, so for this equation, you will get L equal to 42 meters. To calculate for the volume, 42 times 6 times 4. Okay, then the next question, you are to find the detention time. Okay, one things that you have to remember, whenever you calculate the detention time, you have to find always the value of the settling velocity. Do not use the value of horizontal velocity or flow through velocity. Yeah, sometimes it is given and the value is given in the question just to track you. Okay, so whenever you are to calculate the detention time, you have to use L as well as VS. Do not use D per VH. That is wrong. Okay, so in this case, L is equal to 42 divided by the VS, so that you will get about 4 hours lah the detention time. Then check again. VS should be bigger than surface overflow rate, which is 0.003. Yeah, so the uh, the settling velocity, yeah, so the settling velocity is equal to 0.03 is bigger than the surface overflow rate. Where is surface overflow rate? Is here. Yeah, here is 40 meter per day. So when you change to meter per second, otherwise they are not comparable lah. When you change to meter per second, so that you will get 0.003 bigger than 0.00004. Okay, remember in water treatment plant, the settling velocity have to be bigger than surface overflow rate. This is a very quick check, yeah, in the design. Yeah. You know why? Because if the settling velocity is smaller than surface overflow rate, the SOR here is very difficult, yeah, for the colloids or the flocks to settle to the bottom part of the tank. So this is going to be a very quick check lah. Yeah? VS should be always bigger than the SOR. Okay. Tadi, I think that's all. Yeah, that's all on the topics of sedimentation. Okay, oh, sorry, we still have one subchapter. This is on disinfection and chlorination. So in this country, the most common material that we use in build the most common disinfectant, yeah, that normally used in water treatment are known as chlorination. Okay, so it is important, for us to ensure that, yeah, we have supplied sufficient chlorine and there are excess chlorine after the treatment method. You know why? This is very important because having chlorine along the distribution system before it reach our house is important to kill the germs. Yeah, because in water treatment plant we do conducted the treatment. Nevertheless, they should be some excess germ. There should be pathogen that exists along the distribution system. Okay, the purpose of having this process is to kill microorganism which can cause disease. This is known as um, pathogen. It can also be divided into bacteria. It can also be classified into bacteria, viruses, and parasite. Okay, these are the family of microorganism. Okay, it can also be classified into water-based disease, water-wash disease, water-related disease. So these are the terms that normally being used, to explain the purpose of having a disinfection process. So in water treatment plant in Malaysia, we have sometimes they use as powdered chlorine, and some of the advanced treatment system they are supplied into water as a chlorine gas. Okay, so these are the purpose already explained. Apart from using a chlorine, yeah, these are the most common one. The ozone as well as UV radiation can also be used to kill the germs, or the microbes which can cause disease. Okay, so I would like to give a very short explanation on breakpoint chlorination. Okay, whenever you add chlorine into water, yeah, there will be the effect, for the formation of the chloramines. Yeah. After the chloramines has started to kill the microorganism, How do we know that they have killed 99% to 100% of the germ? We only know once it reached the breakpoint chlorination. What is the breakpoint chlorination? Breakpoint chlorination indicates, this is the amount of the chlorine added into the system is sufficient to kill the germ. And in addition, the importance of the breakpoint chlorination is to ensure that we have sufficient free chloride residual. Okay, what is this? Yeah, free chloride residual are the excess chlorine that exists in treated water after disinfection process. Yeah, again, why do we need this free chlorine residual? Because it can help us to kill the pathogen along the way, especially along the distribution system, the service tank, and also before it reach our house. So this is the needs for the free chlorine residual. Okay, the amount of the chlorine that being used to achieve the breakpoint chlorination is known as combined chlorine residual. Okay. Right. Apart from that, fluoride are also being added into water. This the purpose of having this is to improve the dental health of the growing children, and these are the recommended concentration. Okay. Okay. The next one is on the topic of the filtration. Okay. Filtration process is actually just after sedimentation process, before the disinfection process. Before, yeah. Give me 1 minute, sir. So the next process is known as a filtration process. Okay, why do we need this process, and what is the importance and what is the significance of having filtration process? Before we go further, I think that maybe we can watch a video, to explore more about the filtration system, whether it's a deep or rapid ascent filtration. Okay, this one. Okay. Okay. So these are the filtration process. Here, 6 minute video. there's no you can watch the animation, yeah. Okay. Okay, then it will flow into the layer of the filter media. So the one in red as well as the blue are the layer of the filter media. Then it will flow into the main chamber. So the one that come up through number 4 are the filtered water. Are the filtered water. Okay, so this is the point where the filtered water are being collected. Are being collected. However, I would like to share with you. Okay, whenever you collected the filtered water, there must be some impurities which is stick within the filter media. For this reason, backwashing is required. So what is backwashing process? What backwashing process is the process where you pump in air as well as water so that the impurities will come out. So that we can remove the impurities which is stick within the filter media. So this is the function of the backwashing. I will come back to the sub-chapter on the backwashing. So now let's see what is the what is a filtration process. Alright. So filtration process is involve layers of the filter media. For example, in this case, is involve layers of gravel, sand, the anthracite. The anthracite coal works like an activated carbon. Okay, to remove the dissolved material, dissolved solid. Okay, so this is the water level during backwash. So this is where water will flow through. You can see water inlet, it will flow through the layers by layers, and we can collect the clear water. We can collect clear water from filter drain. So this is known as the filtered water. Nevertheless, after certain period, after certain period, after certain cycle, after certain cycle of the treatment process, there must be impurities, which is stick within this media. For this reason, we have to pump in air, air and followed by water through the wash water inlet point. So I would like to draw your attention that the flow of the water, yeah, the flow of the water which is passed through the filter media should be in the opposite direction whenever we conducting the backwashing. Yeah, for example, just now the flow in this way in normal operation of the filtration process, but in during a backwashing we have to do in opposite direction from the bottom to the top, just allow the dirt to be removed. Yeah, so this is commonly being conducted in water treatment plant after 72 hours. Yeah, after 72 hours, but depending on the heat loss. Yeah, later we will be calculating the heat loss, yeah, in this topic. Right. These are the anthracite. Yeah. Anthracite are also known as the activated carbon, yeah, that being used to further improve the quality of the water. Previously, during the old days, yeah, we only use gravel and sand in the filtration process and maybe layers of sand. Nevertheless, these processes only involve the physical treatment process, yeah, where it will remove only the suspended and uh, dissolved material, not much dissolved material. For that reason, most of the newly developed, yeah, water treatment plant, they are equipped with another layer, yeah, of the media which is known as adsorbent. Yeah, this is adsorbent. So the function of this adsorbent are to remove the dissolved material because they have the capacity to absorb the pollutant. They are not exactly a physical process like gravel and sand. Employing the anthracite coal are also a part of the physical chemical process. Yeah, is involved physical as well as chemical process. So this
Uhu. Ehe. Ihi. Apa? Hello Nazri. Mana doktor?
So please accept my apology. Yeah. Alright, now we shall continue. Okay. I will have to share the slide again. Okay. So these are the processes involved during filtration process. So I mentioned just now, employing the anthracite coal, they are not exactly only a physical process. It's a physico-chemical process, physical as well as chemical process. Why do I say that? Because employing these types of treatment technology, which is known as adsorbent, it will absorb the impurities. Yeah, employing these types of technology has also the capability to dissolve, meaning to say that you can reuse the anthracite coal. Yeah, so this is why they are part of the system. Yeah, but nowadays, in order to further improve the quality of water, of the treated water, water treatment operator has also employed the powdered. This one is in the form of granular, yeah, which is smaller than the sand, but in the form of granular. Normally, the size is about 2 mm. Yeah, but in order to further improve the quality during the pre-aeration process, before coagulation process, the water treatment operator will add the same material and anthracite coal activated carbon, but in the form of powder. Yeah, because employing this method can further improve the quality. So this indicates that there are two steps in water treatment process where adsorbent or activated carbon technology are being employed. The first one during pre-aeration process, yeah, during pre-treatment. The second one during filtration process. So the remediation time for the filtration process normally it will take about 2 to 5 hours. Yeah, it will take about 2 to 5 hours. Okay, this is the standard time, yeah, for the filtration process. All right, these are the basic uh, diagram. Yeah, this is the feed water, meaning to say that the untreated water, you can see, yeah, the impurities will stick within the pores, yeah, of the filter media. So the water which has been filtered is known as filtrate. Yeah. Okay, employing the filtration system can promote the formation of the bed sand, of the sand bed. Yeah, this is in German. Yeah, I don't know how to pronounce this, but I believe that our friend here, Torben, yeah, maybe have a better pronunciation of this dirty skin layer. Yeah, dirty skin layer normally will be developed due to the reaction of the chemicals, biological substance that exist in untreated water, yeah, after sedimentation process. Yeah, so this layer uh, uh, has the advantage, yeah, advantage of having this layer. It can absorb and straining the impurities. Yeah, so uh, but this is very natural process. It will be developed after a certain period. Yeah? But the function of this layer is to absorb and straining out the impurities. Yeah? Okay, this is the filtration system, the real photo of the filtration tank. Yeah? Alright, I would like to share with you the video on the backwashing process. Backwashing process is the most important process waste in water treatment plant. Because this is the process where the impurities that exist within the filter media can be removed. There is no voice, so that I will reduce the sound level, but you can read the explanation. So I mentioned just now, when we would like to conduct the backwashing process, we have to blow the air as well and followed by the water. Yeah? This is in the opposite direction of the water flow. Okay. And this is for 8 minutes, combined air and the water pump. Okay, then stop air, continue water pumping for rinsing all dust. This is for 7 minutes until the water is clean. First, pumping the air, then combine pumping air and water for 8 minutes, then for 7 minutes only water. You can see, they have now stopped pumping the air, only the water. Okay, now it's getting cleaner. Okay, step 4, backwash, finish, open water bath, back to filtration mode. Okay, so in short, yeah, whenever there are water flow in this direction, yeah, from the rectangular tank into this channel, this indicates that it's a backwashing process. Yeah, so for a normal filtration process, yeah, for a normal filtration process, water will flow, yeah, in this way into the filtration system. So this is how um, the system works. Yeah, it's always in opposite direction. So here in this rectangular tank, in the rectangular tank, there should be layer of the there should be layer of the filter media. Okay. So there are two major system, yeah, of the filtration. The first one is known as slow sand filtration. The second one is known as rapid sand filtration. Slow sand filtration are no longer used in conventional water treatment plant in this country because it's require maintenance, frequent maintenance. However, there are many, yeah, there are many portable treatment system where they employ a filtration process. The slow sand filter still um, being used as a part of the treatment. And so this is the oldest type, yeah, of the large scale filter. The layers of sand about 36 inches, yeah, and the sand remove particles from the water through adsorption and draining and straining. Okay, so for a slow sand filter, the major difference, yeah, between the slow sand filter and the rapid sand filter are the filtration rate. These are the major difference between these two types of filters. That's why the slow sand filters are no longer applicable in conventional water treatment plant because of the low filtration system, yeah, low filtration rate, yeah. So the use for the removal of turbidity, yeah, they are good for the removal of turbidity, but employing the slow sand filter can improve the quality of the water, not only in terms of the physical parameters as well as the chemical parameters. Employing the slow sand filter can also improve the quality of water in terms of bacteriological parameters, yeah, because this system has the ability to remove the E. coli as well as the coliform, yeah. So it can be used to replace the coagulation, flocculation settling. Yeah, it can filtered water has less than 0.3 NTU. Yeah, so output water may require chlorination. Okay, and maybe is require also pre-treatment. Yeah, so these are the cross section of a slow sand filter. They are more or less the same to the rapid sand filter, but the difference is in terms of rate. And the slow sand filter, we don't have any activated carbon layer, but activated carbon layer can be employed in a slow sand filter. But the slow sand filters nowadays, they are no longer used in a water treatment plant. Okay, the advantages of employing this system is simple to construct, cheaper, physical and chemical improve in terms of these three parameters and reduce the bacterial count. It's about 99% of the coliform and 99.9% of the coliform and 99% of the E. coli. E. coli are the indicator of the waste. So all fashion, but it's old fashioned and outdated lah. Initial cost is low, but it's require frequent maintenance. And this filter needs a lot of space. Okay, this is the existing innovation that being applied, that currently used in water treatment system. However, when you employ this system, we have to conduct the backwashing process. So the major difference again is the filtration rate. The advantages and disadvantages is there are more. There are more advantages of applying the rapid sand filtration. It can deal with raw water directly, occupies less space, filtration is rapid, washing of filter is easy because we can simply conduct the backwashing, and more flexibility in terms of operation. Nevertheless, dealing with RSF, relatively high skill operation, more cost and remove bacteria not as much as the slow sand filtration. Okay. So normally when we employ this method, sands are the popular media to be used. So these are the recommended. Let's say gravel will be the lowest, not only to filter the material but also to hold the entire structure of the filter media. Yeah, so we have here the gravel, the size about 5 to 60, the specific gravity of the gravel. So the size of the sand is about the diameter, 0.5 to 0.55, and the depth is about 45. So the anthracite, the activated carbon, the size is bigger, 0.7. Um, the depth is 30. So but in terms of the specific gravity, this is the lowest lah. So in terms of weight, anthracite is the lightest one. Anthracite is the lightest one. So that we arrange the configuration for the filter media arrangement are based on the specific gravity. So that the heaviest one will be at the bottom, because we would like to hold, it has to hold the entire structure of the filter media. Okay, so it should be dirty from the dirt finally. Okay, so these are the rapid sand filtration during normal operation water filter. So we have to close the valve, so because to collect the filter water. However, during backwashing process, the filtered water valve will be closed and we can apply the backwash process. Okay, so this again the cross section when the normal operation of filter as well as during backwashing process. You can see, in some system they employ the same outlet. Let's say this is the outlet for filter water. After filtration process, the same outlet they will flush in the air as well as the water during the backwashing. So uh, it depends on the configuration of the system, but the water inlet and the backwash dirty water outlet are in a separate room lah. Okay, this is to design for a slow sand filter. This is again, you can go through this one because this is more or less like how to design the sedimentation tank just now. For example, design for a slow sand filter to treat about 800 meter cube per day. Okay, to design for a slow sand filter, we are to refer to the table. These are the recommended range in terms of the filtration rate, the height of the filter bed I put in purple, as well as the height of the under drains layer, which is the gravel layer. So the supernatant water is allowed about 1 meters. So in this case, the filtration rate is about 0.15, referring to the table. So the required tank area, knowing the value of the flow rate, the required tank area is about 222 meters squared. Yeah. So choose this is the proposed size, about 23 meters long and 10 meters wide. Yeah. So based from this table, so that you can propose the system under drain height is about 0.5. So these are the maximum here. Yeah. And the next one is height of the filter bed. Yeah, height of the filter bed here. And also height of the supernatant water as recommended in the table lah. So in total, 0.5 plus 0.9 plus 1, the total height is about 2.4. So that these are the recommended tank size for the filtration system. Okay, apart from that, you can also come up with the sizing of the tank based on the detention time. So as I mentioned just now, the detention period, for a filtration tank, you can come up with the sizing of the tank based on detention time. The detention time for a filtration process is normally about 2 to 5 hours. So I think you can go through this example yourself. The difference between this table and the previous table, this involve wool media, yeah, anthracite as well as the sand. Okay, so uh, again, this is the cross section when the operation of normal filtration process as compared to the backwashing process. Alright, so when to conduct the backwashing? Okay, this is extremely important. Yeah? Extremely important to know when to conduct the backwashing. According to the guideline from the water operator, the head loss, when the head loss reach 2.1 meters or reach 72 hours, which one first, then backwashing has to be conducted. This is important. Okay, how to know the head loss? We have to calculate what is actually the head loss. Yeah? The head loss is the layer of water above the filter media. For example, this one. you know, you know what? Yeah? When there are impurities stick within the media, there will be higher head loss. Why? Because no more space water to stay within the tank. Yeah, that's why I said the more the impurities within the filter media, the higher will be the head loss. So this is what that we have to properly monitor. Once the head loss reach 2.1 meters, so the backwashing has to be conducted. Or even though it has not reached 2.1 meters, but is reaching to 72 hours, so still backwashing has to be conducted. So these are the real indicators in water treatment plant. Okay, so normally when they receive the low quality of raw water, definitely they have to conduct frequent backwashing process. Okay, so to clean the why backwashing is important, yeah, to clean the filtered impurities of the particles, yeah, because you flush out the impurities. Yeah, so how to calculate the head loss? Yeah, there are two ways. The first one is known as Kamen-Kozeny equation, which you have studied before, and the one that we are going to explore today is known as Rose equation. Rose equation are actually more popular. You know why? Because it's involved. It can be used to represent more than one types of the filter media. Kamen-Kozeny represent only one type. Yeah, so that rose is more preferable. Okay, persamaan rose. Yeah. So this is the comparison. Maybe we can see the example before, yeah, on the two slide more. Okay, maybe we can see the example, yeah, the example on how to calculate for the um, before we look at the example. So this is my handwriting on the my quick uh, schematic diagram, yeah, on the concept of the backwashing. Yeah. So what this is during filtration process, water in from sedimentation tank. Yeah, this is from sedimentation tank. It will pass through. You have to follow carefully. Yeah, the arrow. Yeah, the arrow. It will pass through the anthracite or the activated carbon, sand, gravel, and it will come out as the filtered water. Yeah, so that after few cycle of the operation, yeah, because we will allow water to stagnate before it will pass out the system, you can see that the head loss will be higher. Yeah, head loss means to say that the layer of water after the filter media, on top of the filter media. So this is the level that we have to monitor. The head loss should be always less than 2.1 meters. If more than 2.1 meters, that indicates that too much impurities stick within the filter media. For that reason, backwashing has to be conducted. Or it has not yet reached but already 72 hours, again backwashing has to be conducted. So this is the process happen during backwashing. Pressurized water will pass through in an opposite right direction. So we have to apply a correct velocity, yeah, which is known as a backwashing velocity. How to define the backwashing velocity? The backwashing velocity is the velocity which is strong enough, yeah, which is sufficient to remove the impurities within the filter media, but not strong enough to remove the media, because we would like to only remove the impurities. Yeah? If the velocity is too high, it will remove everything, including the filter media. Okay, so we have to be careful when selecting uh, the backwashing velocity. Okay, so let's go to the example. First, we look at the shorter example on the Kamen-Kozny equation. We have go through this example before, and after Kamen-Kozny, then we shall explore on the Rose equation. Okay, this is to calculate the head loss. Yeah? So we have to calculate the head loss because knowing the head loss will tell us the needs for the bed washing. Okay, determine the head loss across a bed of a uniform size particles. Clean water at 20 degrees Celsius is pressed, yeah, into a bed uniform sand at velocity of 5 meter per hour, which is equal to 1.39 times 10 to the power of minus 3. The sand grains are 0.4 mm in diameter. Okay, so dealing with Kamen-Kozny equation, you can have uh, uh, you can only have one size of the media. Yeah, one size of the media. So for example, this one is the sand with a 0.4 mm diameter and the shape factor of 0.85 with the SG of 2.65. The depth of the bed is 0.67 meters with the porosity of 0.4. Determine the head loss. Okay, you are given the dynamic viscosity equal to 1.002 times 10 to the power of minus 3 kg per ms. This is the density. You need this value. You know why? Because you are given the dynamic viscosity. Yeah, to calculate the Reynolds number, rho Vd over mu or Vd over nu, yeah, the kinematic viscosity. So if the kinematic viscosity is given, meaning to say that you don't need the rho value here. Yeah. So you solve for this equation, you will get the Reynolds number. Then you can substitute into these two equations. First, you calculate the friction. Yeah, 150. This is the fixed numbers. 1 minus alpha. Alpha is the plus 175 over Reynolds number. Alpha is um, alpha is the 1 minus 0.4, the porosity. Yes, alpha here is the porosity. Yeah, it's not the size of the grain. The porosity here are dimensionless, yeah, because the porosity is a percentage. Yeah, so over 0.47 plus 1.75, you will get 190.24. Then knowing the value of the friction, you can substitute into the head loss equation, Kamen-Kozny head loss equation. So the friction times the depth, yeah, I put capital D because we do have D here. D, the small d represent the diameter, while the capital D represent the depth. Yeah? So 1 minus alpha, again v to the power of 2, v is given in the question, alpha is also given, GD is also given. So you have to calculate the friction, yeah, so that you can substitute into this equation. So in this equation, the head loss is is about 0.6 meters. Okay, this is one method, very simple method to calculate the head loss. Okay, let's see the other methods, yeah, that can be used to calculate the head loss. The question is here. Okay, okay. Compute the clean water head loss in a filter bed, yeah, for a filtration rate of 150 liter per meter squared per minute, given the porosity and the shape factor of the sand is 0.5 and 0.65 respectively. Present this finding using Rose equation and the kinematic. In this case, you are given the kinematic viscosity, yeah, is equal to 1.02 times 10 to the power of minus 6, and the depth of the filter bed is equal to 0.85. To solve this kind of equation, and normally I will provide this table lah. Yeah, I will provide this table. So you are given the sieve size, the fraction sand retained, and as well as the diameter, yeah, of the sand. Okay, so you have to calculate the Reynolds number, the drag coefficient, in order to get the head loss. So the solution is longer lah, yeah, for this when you use Rose equation. Okay. Uh, Here. Yeah. So this is the final example. Yeah. All right. Quiz is raining heavily here. All right. Filter bed for a filtration is given in the question. Porosity is given. The shape factor is also given. This is the kinematic viscosity. The depth of the filter bed is 0.85. You to for this is I think I will provide the table, but my suggestion, if you have extra time, then you can copy the table, yeah, in case the question will come out in the final exam or test. You copy again the table, but if you do not have ample time, you can simply use the table provided in the question. Okay, 1, 2, 3 are provided to you. Yeah. So number 4, column number 4, Reynolds number, you have to calculate. Yeah. So you can try, to calculate the Reynolds number. Yeah. So how to calculate the Reynolds number? In this case, yeah, let's see. Comparing between the equation for the Reynolds number, this one is VD over kinematic viscosity. Yeah, the previous one, we used rho VD over mu. Why? Because it was a dynamic viscosity. So in this, you have to be very careful. Depends on the which types of viscosity provided to you lah. Yeah. So in this case, you don't need the value of rho, the density, because only the kinematic are being used. So in this case, first use what the first step is to change, yeah, from liter meter squared per minute to meter per second. Okay, this is the unit conversion lah, yeah. So meter per second. Next, we have to fill up column number 4, which is to calculate the Reynolds number, yeah, VD over kinematic viscosity times the shape factor. If the shape factor is not given, because the shape factor is always dimensionless, there is no unit, so that you can take as 1 lah. In this case, is given as 0.65. So D is always the unknown. This value is given, V is given, you have just converted, and the kinematic viscosity, yeah, so that you can calculate the value of, you can substitute, yeah, the value of D given in column 3, so that you will get the value of 3.55. Yeah. So for this session, I want all of you to try whether you can get or not 3.55, because this question is very easy, yeah, extremely easy, And I hope in case that is come out in test or final exam, all of you should be getting full marks. Yeah, because it's very easy, it's longer but very easy to get a full mark. So now I want all of you to try using this equation, try to substitute the value of the diameter given here, check whether you can get 3.55 or not. Okay, do it now, 5 minutes. Okay, try. Okay, the question are given, the information regarding on the diameter are given in unit of mm. Okay, so that's why we put 10 to the power of minus 3 here so that we can standardize the unit to meter. Okay, anyone, did you manage to get 3.55? All right, great. Yeah. I mean to say that you can solve the following. You should be able to get the following until 0.83. Please let me know if you have difficulties to get 3.55 here. Okay, because this is extremely simple, and I wish everyone to get full marks for these types of question. Next one is to calculate the drag coefficient. The drag coefficient, you have to use this equation. Yeah. Um, 1.0, you have to use this equation. So the Reynolds number that you have calculated, 3.55 just now, substitute into this equation. 24 over nr, which is the Reynolds number, plus 3 over sed nr plus 0.34. Okay, so you should be able to get 8.69. Can someone confirm? Can someone try? Make sure that you can get 8.69.
8.69, Doctor.
Alright, great. Okay, so thank you very much. Alright, so the following step to calculate is to complete the final column, which is column number 6. Column number 6 is CD in bracket rho over D. Okay, in bracket rho over D is this one. Yeah, rho is the fraction, not rho is P. Yeah, P, fraction of the sand retained. Yeah, fraction of the sand retained. So CD in bracket 0.01 divided by the diameter. So can someone try to confirm that you can get 38.97? P here is the fraction sand retained. Sorry, I have to speak louder because it's raining heavily here. Okay, can you get 38.97? Can you get 38.97?
Yes, doctor. 58.7.
Okay, I believe that you managed to get 38.97. Anyone can, someone can confirm? Oh dear. Are you still around? You are still around. And can someone confirm that you can get 38.97?
Dapat doktor.
Okay, dapat. Okay, great. Thank you very much. Kat mana saya tadi? Alright, so when you solve for each of the rows, you should be able to get more or less the total one is the total is 30,870. Sometimes there are some discrepancy lah. Some of the student will get about 30,700. Some of the depends on the decimal point along the way. So the summation, the value might be different now, but slightly different only. So when you have got the summation, you substitute into this rows equation. So the longer calculation, the few steps that you have conducted before are required, because employing the rows equation, you need the summation value to be included here at this point. So they say more or less the same equation, but LV triple of 2 divided by alpha. Alpha is the porosity times G, the gravity, that times the summation just now that you have calculated. So in this case, HL is equal to 0.66 meters, the head loss. Alright. Is there any question? Any question? No question. Alright, so I think that's all for today. Because it's raining heavily here. Okay, don't forget to sign in your attendance. So I'll see you all of you inshallah next week. And we shall start. Let's see. Let's see. But uh, for the time being, I think we do have 21 students, and we shall divide into 3 sessions. For this reason, next week, 7 of you will be conducting the presentation. So maybe the first 40 minutes or maybe the final 40 minutes we will spend on the presentation. So 7, I need 7 volunteers. No worries, everyone will have to submit in Putra Blast next week, but the presentation will be divided into 3 sessions. 3 sessions. Okay. Okay. Oh, yes. In the assignment, it stated that you have to present the maximum of 7 minutes. 7 minutes or 6 minutes, I can't remember. but you have to prepare about 5 to 6 slides. Okay, you check again my question. Yeah, I have stated that you have to present within 5 to 6 minutes, if I'm not mistaken, to prepare the slide, about 5 to 7 slides only. Yeah, very short and simple assignment. Yeah. Okay, get ready to submit next week in Putra Blast, but only 7 person are going to present. Oh, thank God that we have only 21 students. Okay, all right. So thank you, everyone. Wish you to have a very pleasant evening. Yeah. So have a nice day. Bye.
Alright, thank you, Doctor.
Thank you.
Thank you,
Bye.
Doctor.
Thank
Thank
you,
you,
Doctor.
Doctor.
Bye.
Thank you.